Okay, so understanding the layers of the CMOS transistors and semiconductor materials or devices is very critical, super critical for understanding any future design using different technologies. So we have to cover this kind of material in this class. It serves for a lot of different purposes. And that's why if you look at the in-class exercise, it has all these examples for drawing the cross-sectional view of the layers of a transistor, or probably it's not even the transistor, just something on the top of the wafer. Okay, so it's a very classic structure, not being changed too much, even for the very modern devices. Okay. And there's a quiz on Wednesday. We keep in mind we don't have a homework assignment between Monday and Wednesday, so you have to rely on yourself to go through the notes and videos to practice all these C5 layers. So that's why I'm giving you an in-class exercise so you can practice on that paper to prepare for the Wednesday's quiz. It's going to be exactly this, not exactly, but very similar materials or problems on the quiz. And this is pretty simple. I will let you know what that's going to be. And there will be some homework, C5 layer drawings and similar problems in homework 2, but it's due next week.
Will the quiz on Wednesday have any PN junction problems?
No.
Okay.
Mm-hmm. This is related to the lab from last week and also this week. We have been doing NWEL resistors, and you probably don't know what NWEL is. If you look at the wafer from the side, this is a cross-sectional view of the wafer. It's actually really thin, but I'm just drawing it to make it visible. So the NWEL is just N-type material being doped into the wafer. Usually this wafer's material is P-type, for example. P-type. P-type means we have wood being doped into the wafer. P-type. Remember? Boron, right? P-type. The P-types is P-type wafer, or we call it P-sub. It's a P-type. P-type substrate for all the devices to be put on the wafer. And we can dope a well. It looks like a well, but it's just something being diffused into the wafer. You can put a wafer in a certain environment, like high pressure, high temperature, and then you evaporate the N-type material, the molecules, into the chamber, the vacuum chamber, and high pressure, high temperature. So under a certain condition, it will diffuse into the wafer, and you can have there will be something on the top that can block. So when you do the diffusion, it's actually you can deposit a certain pattern on the top. So eventually, these are blocking that dopant of the N-type material. It's not because it's blocking it. So only this opening. So this area has the opening, so it's able to accept all these dopants. So it's getting diffusing into the wafer. That's how that works. And so we can use a lot of technologies to block it. So it's called photolithography, including the photoresists, including metals pieces, including all the other things. And Gavin did a lot of these microfluidic wafer photolithography. It's very similar to the semiconductor chip design process, even though it's way easier. But it's a similar process. So eventually you can just define a certain type of NWEL in there. For example, the ones we have been using, or during the lab tomorrow, it will be just a strip, okay? Or you can call it just a wire. just a piece of wire. So you can actually define that certain shape to be put in the wafer as unwell. If you have a contact over here and contact over here, okay, metal wire, and this becomes a resistor because this certain material has a certain resistivity. And if you look from the top, for example, this is your layout of the chip design, and it looks like this. Okay, you have a contact here, you can connect wires to it. That's the top view, and this is a side view. It's a cross-sectional view, side view. Right? So this certain shape, because of the material or the process of the foundry, when they are doing that dopant, putting that dopant into the wafer, they are following the same protocol. It's not always changing the pressure or the temperature and changing the processing time. It's actually a constant. It's not changing. So in that case, the depth over here will be a constant. It's not changing. Okay, just to let you know. According to a certain process, a certain unwell device will have a certain depth in there. It's not changing. Definitely, there might be a different unwell. Could be unwell 1, unwell 2, unwell 3, but assuming that we are using the same unwell all the time. Okay, it's not changing. So in your layout, this is your design. When you are designing it, you can make it thicker or longer, depending on your needs. Okay. So we all know that for a certain wire, I know the wire could be a rod, but now let's just assume the metal wire, the shape of the wire looks like this. Okay, that's the wire, and here's the depth. Let's call it thickness T, and this is the width. This dimension is the width, and here's the length. If I got a wire here, I'm measuring the resistance or resistivity of this rod, probably. And the resistance equals what? Equals resistivity times L over A, right? That's a cross-section's area. And here's the length. By definition, that's the resistance. This is resistivity, is a constant of the material. Here's the length, here's the area. And the area equals the width times the thickness. Okay? And this also equals this. Why I do this? Because the resistivity is from the property of the material, which is a constant, and the thickness is from the process is also constant. So the conclusion here is, if I have a square, little square, like here for example, because length and width, so here's the thickness or depth. My question for you guys is, when I'm doing a layout in a electrical VLSI, I'm laying out which dimensions. I'm changing here. What are the dimensions that are being changed?
It's the length and the width, not the thickness.
Yes, length and width. So basically, this rod is this guy from the side. If you look from the side, okay, I'm actually extracting this unwell resistor here. If you look at individually, it looks like this. And here's the depth. If you're doing layout design on the top, from the top view, you're only able to see L and W, right? Instead of thickness. Thickness is going into the paper. It's not really visible. So in that case, if I draw a layout like this, a little square, I'm assuming this is a little unwell resistor in the layout view. Okay, I'm measuring it. I got a resistance. And also I'm drawing a bigger square and measure it. Do they have the same resistance?
No.
Why and why not?
Well,
So Here's the length. Here's the width. Depth is a constant. We don't care about that. Okay, it's a constant. It's not changing.
Yes.
So when we do the layout, we are laying out the width and length from the top. So here's the layout from the top. Length, width. Length, width, the same thing.
Is it the
Are
same-
we getting the same resistance?
Yes.
Why?
is it- It's the same ratio or is it scaled up?
No. So L over W is the same rate, it's the same length, right? It's the same length. Length and width are same. So this equals what?
That's just
1. So it's gone. So R equals what? 2 constants.
Yeah.
So little squares, bigger squares, they have the same what? Resistance. And this is called the sheet. So a square when L and W are both are the same, and resistivity divided by the depth is called the sheet resistance of the unwell. Sheet resistance. And for the, I believe for the C5 process we're using, for the unwell we're using, it's 800 ohms per square. Per square, because every square has the same resistance. So it's 800 ohms per square. In that case, when you're calculating resistance of the unwell resistor, you're laying out, you actually count how many squares do you have. Okay? How do you count how many squares do you have? You know the length and you know the width.
Yeah.
How many squares do you have over there? It's just length over width. Isn't it?
Oh, yeah.
Right?
Yeah.
It just length over width will give you how many squares do you have.
Yeah, because they're all laid out in series, right? So you can just.
Yes.
Yeah.
So even though you don't divide them into squares, you directly draw a length. You draw a length and also define the width. And eventually the length divided the width will be how many squares do you have. And then you times the sheet resistance, eventually you get a resistance of the unwell. That's how you design a resistor with the unwell. Okay. Here's one example. Oh, another question for you guys. If let's just draw it first. So I got this guy, and I got an unwell here from the side, and contact wire. So eventually, this becomes a resistor. This is a resistor, and also remember that we have a pin junction. Why is a pin junction? Because it's a P-type. It's unwell. So even though it's not exactly the shape we learned, but it's a pin junction. It's going to form a pin junction over here. Okay? It's forming a pin junction over here. So the pin junction, remember that there's a capacitance in the middle. And the name of the capacitor is called, because this has a certain width, and we are considering this is a metal, this is a metal plate, this is a metal plate, and this is forming a capacitor called CJ, and it's a junction capacitor. So that's why when you are having a circuit, for example, like this, that's the power supply. Have a resistor which is limiting the current, so it's not burning that diode. Okay, you have a circuit like this, and you are driving this one using pulses, and you're expecting what over here?
Delayed response.
Time delay, because this has a little cap inside. Okay, there's a capacitive load inside the diode, and that is why. So for this one, you have parasitic capacitors over here embedded in here, like this. And so we can model it in a way like this. So within the N-well, we can model it they are all shorted to ground, and these are all the we divide it in this way because we want to use R square as the sheet resistance, and here's a V, here's VL. So for the N-well resistor, it's actually not ideal. It's not just resistor, it's RC circuit. So the N-well resistor will introduce time delay, just to let you guys know, because of the capacitors over here. Okay? So in that case, how do we calculate the time delay though? Here's V in, here's V out.
Did you just do superposition again?
Superposition, yeah, that works. A similar theory. If you look at this one, let me give example. So here's the model. Here's the example. The width of the N-well is 10. Doesn't matter 10 what. Okay, so we are using. Yeah, let me let you know this. So lambda is 300 nanometers, and that's the unit we have been using. We will be using for the lab for the whole semester in electrical VLSI. It's a very simple concept. So whenever you are seeing a number here like 5, it's actually 5 lambda. It's just a unit. Why do we use 300 nanometers as a lambda? It's called the lambda rule. Yeah, because C5, 5 means 500. Okay, and 500 nanometers. And the smallest transistor or smallest feature you can make in this process will be 500 nanometers, no matter what, in theory. But the thing is, a lot of times we don't really want to hit the limit. It's going to reduce the yield, which is like if you make 100 chips, maybe only 80 of them are functioning. So in order to keep the yield high, so we define a lambda rule. This is a really old rule. People have been using, since the 1970s or 80s probably. But we are, just learning the basics. That's why we are introducing this one. But we are transferring to or shifting to TSMC 180. Will be totally different design rules. But now we are just still talking about your grandpa's age, whatever rules over there. So lambda rule 300 nanometers, and the minimum transistor width or length we have been using, we will be using will be 2 lambda, and this becomes 600 nanometers, which is slightly bigger than the limit of the process to keep everything functioning. So that's why we use lambda for 300 nanometers as the design rule. So it's multiples of lambda, but the minimum is usually 2 lambda. All right. So when we are talking about this, we don't really need lambda, but you need to know that if we are using this number in electrical VLSI of the layout tool, this actually stands for 10 lambda, because a lot of times you see a transistor labeled as 20 versus 10, but doesn't have a unit with it. So you need to know that it's actually 20 lambda times 10 lambda. Okay, so this one doesn't have a unit. It's actually 10 lambda, for example. Right? It's 10, and L, the length of the N-well resistor is 500, and the resistance of the resistor is 250k. Is right given, 250k ohms, and also it's given that 10 by 10. Again, just ignore the unit. A 10 by 10 capacitor. Capacitance a piece of N-well's capacitance. Okay, so the 10 by 10 capacitance of N-well is 5 femtofarads. It's asking you what is the what's the time delay. from input to output going through this unwell resistor. What is the time delay going through this unwell resistor? So given that you know the resistance, right? And it's given that L over W is 500 over 10, which is 50 squares. 50 squares. And 50 squares is giving you 250 kilo ohms. So you can find the sheet resistance of the unwell resistor. R squared equals R divided by 50 squares. It's giving you 250k ohms divided by 50 squares, which is 5 kilo ohms. So the sheet resistance of this unwell is 5 kilo ohms. And it's telling you that 10 by 10. So because the width is 10, so it's making things a lot easier. So the width is 10, so 10 by 10 capacitor of the unwell. So the capacitance underneath that 10 by 10 piece of unwell is 5 femtofarads. So how many squares do you have over here? 50. So should you add them together or subtract from each other for capacitance? So capacitance equals what? Epsilon A over D, right? D is the distance. You have two plates. Here's the area. Here's D. That's a constant, epsilon. So this is the top view, and this is the set view. If you're doubling the A here, you're doubling the capacitor. If this go up, this go up. Here's the unwell sheet from the top. That's the top view. When I'm putting more squares next to it, it's basically putting more pieces, more area next to it. It's actually increasing the area. If you have 50 of these squares, you are actually have 50 times of the capacitance. Okay, but now it's okay because if you look at the model, we actually divide it into all the little pieces. It's a C square, even though C square is not a constant. But we are using a C square for this case, just for this case. And the time delay for this model is calculated as, it's very interesting. If I label it, for example, I label here, let me draw it. V in, if you have this type of circuit, RC, RC, RC. So they're asking you to calculate the time delay. We know the time delay, how to calculate the time delay over here like this, right? So if we label this point as A, this is B, C, D. So A to B is just simply 0.7 RC. So what about A to C? It's getting a capacitor in the middle. It's making things complicated. But the way we do that is we just calculate, we just adding all the contributions of the time delay of the cabs together. For example, if you're just looking at time delay contribution from this one, it's just a 0.7 single R, single C, right? Then we just disregard this guy because its contribution already calculated, it's already counted. And now we disregard this guy and only look at this guy's contribution from A to C. So what is that? Because, yeah, 2 RC, right? 2 RC. And what about this one? 3 RC. Yeah. So total delay will be A to D, right? A to D. 0.7. No, actually, the contribution, all of the contribution has to be added together, right? It's going to be 0.7 RC plus 0.72 RC plus 0.73 RC. And this becomes 0.7 RC times 1 plus 2 plus 3, okay? So what about you have n, not just 1, 2, 3, but eventually a lot. And n of them, n stages. So usually, whenever it's longer than 10, we consider it's a pretty large n already. And it's really easy to reach. So you got a 10 squares, it's a large n. So we really want to draw a conclusion from that because of, most of the NR resistors are actually pretty big. So what's the conclusion can we draw from here? If it's an n, then it becomes 0.7 RC, 1 plus 2 plus 3 plus n, and this becomes 0.7 RC. I think the equation for this one for summation is 1 plus n over 2. Is that correct? Mm-hmm. The first value added to the last value and divided by 2. Forgot. I think this is on my notes. I think that's probably right.
Oh, so it's n plus n minus.
Oh, times L. Times n. So, yeah, got it. So when n is large, so when n is close to infinite, then it's 1 plus n times n divided by 2. That's just an equation existing. We don't have to dig too deep into it. So just calculate the summation from 1 plus until n, then the summation's equation is 1 plus first plus the last and times the number of numbers in there and divided by 2. So that's how you calculate it. And this becomes, so 0.7 divided by 2, you're getting 0.32 R, and 1 plus, wait.
It'd be n plus n.
Oh, so the thing is, because n is considered large, for example, it's 10, right? So 10 times 11, we can just use 10 times 10. So you can directly put an n square over here as a approximation, which is fine because we consider n is large. So n is large, so 1 is super tiny compared to n. So just ignore 1 over here. Just eventually becomes n times n. Okay.
Shouldn't it be RC?
Yeah, RC. Thank you. So what is exactly n here?
The
Number of squares. So within that, since given that conclusion, I mean 3 of them is too small, but I think I have an example with a bit more. So for this one, we have how many? 50, right? So 50 is definitely a lot larger than 1. So I think we can definitely use this equation for to calculate the result from here. So given that equation, what is the time delay can be calculated from this example? Replace n with 50, right? And r squared is already calculated, and replace n with this number, and c squared is also calculated. It's given actually. It's 5 femtofarads. So we have all the numbers available for the calculation. Any questions on this? Okay. Watch the video if you're not getting it. Okay. There will be problems on the homework assignments, very similar to this one. So knowing that is important, and then we we'll get into the layers of the C5 technology. It has 3 metal layers, which is the first thing you need to know, metal layers. From its bottom up process, then first you have a P-type substrate, and this layer on the top of it is called a FOX, filled oxide. It could be confusing for the first few weeks, keep in mind, because the filled oxide, sometimes there will be an opening on the filled oxide, because for N plus and P plus materials, it will be able to open up the FOX and dope materials into the P-type substrate to make transistors. Could be confusing, right? So what is N plus and P plus? You guys will know that in a bit. But now, just let you know that if there's no transistors being put in the wafer, and there will be an oxide layer, most of them are silicon dioxide. It's an insulator being put on the top of the wafer, and then there will be a layer. It's called poly. It's polysilicon. It's polysilicon. So that's the area to have the gates of the transistors. And then it's a metal 1, metal 2, and metal 3. So the metal layers are not occupying the entire layer. So for example, metal 3, it's just a metal layer over here, and for the rest, it's just a silicon dioxide. It's an insulator. So you can insulate between the metal layers, so they're not having any crosstalk between them. Same to metal 2, right? Metal 2. It's metal 2. Metal 1. It's just metal wires, like the circuit board have the traces. It's metal wires. Polysilicon, the polysilicon is a different type of silicon. It has a certain resistivity. It's conductive, but not as conductive as metals. We use this material for gates or resistors. So you can use several different materials as resistors. You can use NWELs, you can use polysilicon, you can use all different things. They just have different sheet resistance. So when you design your resistor, you need to consider that. It's pretty simple. And for polysilicon, you have 2 polysilicon layers, and one is on the top, and one is at the bottom. And it's called P2 and P1. So I think the bottom one is P1, and the top one is P2. And they're all inside that silicon dioxide, the insulator. And keep in mind, all these are insulators. That active material is just something being deposited into that material. It's like the fillings of the cake you can buy from the grocery store, right? Something being put inside. And these are just running traces inside that insulator layer. And that's the filled oxide. There won't be anything can be put into it. But whenever you are making transistors, you need the opening of the wafer, because you need to dope the dopants into the wafer. So you need the opening on the filled oxide. Otherwise, all these dopants will be blocked. So you have to open the opening over here. So these are all the layers available for C5. And you guys are going to sign an NDA for using TSMC's process, the PDK, for using on Cadence in the future. And that one's a business secret from TSMC. I couldn't even talk it during the class, since I'm recording and posted to YouTube, right? Even though it's I think TSMC 180 was developed in 2005-ish. It's already like 20 years. But still, it's a secret of TSMC. So but definitely, it's a common sense. Definitely, you know that there will be more metal layers in more modern processes. I mean, TSMC 180 is not super modern, but still a lot more layers than this. And the most popular ones, including 28, 28 nanometer technology from TSMC is even more. I mean, almost double from 180, and going down to 5, and there will be. I mean, the number is just like, I don't know, I couldn't tell you, but there will be a lot more than this, you know. So you have more capabilities to route the traces on the top of the wafer. So that's the goal, because it's highly integrated. You have a lot more transistors in a smaller area, so do all the routing so they're not shorting to each other. You need to create a lot of layers on the top so you can drill a hole to the top and route it instead of do this. Does that make sense? Just need more layers, like a PCB design. Same thing. So the PCB you are making is mostly just 2 layers. You have a top layer to route traces. If there's like short circuits, then you just dig a hole here to the bottom layer and then route tracer and then come up. So you can imagine if you have like 40 layers of the PCB, you can highly integrate all the components on the smaller area. That's the motherboard of the desktop. It's probably like 20-something layers of PCBs. I don't know. Right? So all the undergraduates are still making two-layer PC, which is fine. I mean, Build the Tools does all the drilling. You are naturally manually drilling the holes, so it's okay. Now let's start looking at some examples of the layers. If I have let's say metal 1 and metal 2. I think this could be a reference. Just if you already drew it on your paper, just come back and look at it when we are going through this example. Let's say metal 1. This is metal 1. This is metal 2. That's the layout view. That's the top view. And there's a little contact. It's called a via. It's a through hole. It's a via. To make the connection between metal 1 and metal 2. So metal 1 is running at the lower layer, and whenever you want to make a connection, drill a hole and connect to metal 2, going through this direction. So I'm going to ask you to draw a cross-sectional view of this structure at this line. Do you have N plus or P plus in there? No, just metal layers. So that's why Fox will stay. And this is a P-type. All right, what's on the top of the Fox? Poly. Do you have any poly wires over here in the design? No, but do you still have the insulator? You still need it. Even though, because this area of the circuit doesn't have poly, doesn't mean you don't have poly somewhere else. But even though you don't have poly anywhere, the process will still deposit a insulator on the top of the Fox. It's a standard process. All the layers will exist. Okay? Doesn't matter if you have some traces in that layer or not. The insulator will exist. So that's the poly. And then on the top of it will be metal 1, right? Look at metal 1. Oh, it's a bad drawing, but you'll see that here because this is, I'm going to draw a dashed line to show that the metal 1s starts from here and stops here. And it will be a little bit shorter than the width or the height of the insulation layer. And that will be a metal 1 trace by looking at from the side. So assuming that I cut from the top through this line and then flip it by looking from the side, I'm going to see a metal 1 wire like this. Then metal 2. I'm running out of space. Metal 2. Looking from the side, it's only this wide. Okay? Only this wide. And there will be because this dashed line crosses this via, so you'll see a via here as well. If it doesn't cross this via, you shouldn't have a via, keep in mind. It crosses the via, so flip it, looking from the side, you're going to see a via. So that via is making a connection between metal 1 and metal 2, so definitely it should make a connection. Then metal 3. So you should label that, okay? Metal 1, metal 2, metal 3. And that's it. Pretty simple. And that's why teaching C5 is important. You don't want to teach 5. You need a bigger paper to draw the layers. It's even impossible. Take the exam, final exam, it takes spend all the time just by drawing all the layers on one problem. So what if I draw a line here?
Like
Here, metal 2.
to like cross section.
Yeah, cross section.
I guess draw the layers.
Fox still stay, right?
Yeah.
Poly stay, but nothing. Metal 1 stay, nothing. And metal 2 has something, which is this piece. You got a metal 2 here. Metal 3, nothing. Make sense? Cool. Now let's look at a different example. Different example. Yeah, from the handout. I give it to you. Let's look like this one. It's more complicated. So this is directly a snapshot from the textbook. You can see it drew a. It's so dark over here. But you can see on your paper, right? It drew a line, a dash line here. Dash line here. And you can see the fox is getting opened up. Why is that? So there's something we didn't cover from the last paper.
Is it the insulars?
Yeah, the PI is the transistors.
Yeah.
So something you need to know here, which is P act. Oh, these are just names from the electrical VLSI. These are not exactly the names you use for TSMC's PDKs, but it's just something you need to know. Okay, P act and P select. You'll see this a lot throughout the semester. So these are the two pieces you can find from the library in electrical VLSI. It's just components you can directly use. So what this does is P act, this guy, opens Fox, and P select dopes N plus O, because the P select, so it's a P plus. It dopes P plus within that window. So example here is if I have this wafer and I have Fox. I mean the Fox is not really exactly on the top because it's not really even on the top. So sometimes you can see people draw it like this, just going into that wafer a little bit to understand what's going on, because it's not really flat, it's going like this. All right, so this one is getting open if you have a layer of this P act. It opens up the Fox exactly at here. So why do I draw a little square on the top? Do you know what I'm doing here? So this whole thing here is the top. It can be confusing. So this whole thing here is the top view. So I'm actually showing a layout. A P act surrounded by a bigger square, bigger box, which is a P select. They always come together because P act opens up the Fox, and P select will start doping the dopants into the wafer. So why P select is slightly larger than P act? It's trying to get rid of the misalignment issues, because whenever it's getting to, even though for 500 nanometer technology, it's still small. It's still not like millimeters or centimeters. It's still pretty small. So in that case, when you are putting the masks, so masks is being used for doing all these alignments. So we don't have to worry about all these process, the details of the process, but just imagine for all these features over here, it's probably just like tens of nanometers. Okay? If you use a P select box exactly the same as a P act, so you open up the window here and you're trying to dope the materials exactly within this area, you are expecting some misalignment, then you are actually missing this little gap over here. Can you imagine? So in that case, let's just make the P select a little bit bigger than the window. So even though it hits the flux, but it's not hurting anything because these are just not reaching the wafer. But eventually you can get the whole area of the window, underneath the window, getting doped by that specific material. And that is why P select is a bit larger than P act. Okay? Now let's come back. Same for N wells. Same for the N well. And you can see that N well is bigger than, sometimes it looks different even than flux. I mean, I imagine the N wells are being doped into the wafer before you have a flux being put on the top of the wafer, because you can see here it's getting blocked, but you still have an N well over here, right? Anyway, so depending on the process, it could be different. But now we don't worry about that. We just look at the cross-sectional view of this guy. See if that makes sense. I mean, the in-class exercise is not due today. It's due Wednesday, right? Due Wednesday. So we don't have to turn it in today. So this is example. You look at this whole thing. Here, this box is a P select. The solid with a solid line outline is a P select. And these areas, the shaded areas, are PX areas. So this bigger box, P select. Smaller box, P act. And this thing in the middle is a gate, which is the poly. It's a poly layer. It's a gate. And this is metal 1. And that's a via. So that via is actually from the wafer tool, or we call it diffusion, okay? No matter it's a P plus diffusion or N plus diffusion, it's a diffusion. So this via is a diffusion to metal 1 via, which is this guy. All right, it's on the top of the Fox layer, but within the same layer as a poly. So here's a gate, that's a poly. Because on the top of Fox, you are expecting a poly's layer, right? And here's a poly. The poly is a gate. Polysilicon, which is a gate. So that's why it's a dimension of the gate. Same thing, which is over here. And it's a metal 1. It's a metal 1. Also metal 1. Metal 1. Here's the N well. It's within that wafer. And here's another diffusion. That's the N plus diffusion. And you have metal 2 here, but metal 3 was not drawn. But in your results, please draw all the layers up to metal 3. No, this is metal 2, sorry, metal 2. So metal 3 is not drawn here. Is there N well? Yes, N well. So N well is a big N well, covers everything. And I'm going to explain why we need N well for the P transistors in the future. But now you can see all the P transistors are being put in the N well. Okay, you have a big N well here, and that's for P transistors, P-type transistors. What's that?
This specific one only uses an M1, right? Because I don't see an M2 or M3.
No, M2 is not being used. There's no M2. No, M2 is being used for routing. For the transistors, you just need a metal 1 for a connection to diffusion. It's just like the transistors nodes, right? You have this is the gate, which is the polysilicon. You have drain, source. It's the bulk, which is body or bulk. It's actually the P-type substrate. So that's the symbol of the whole thing, of the whole transistor. And that's cross-sectional view of the transistor. That's the symbol of the transistor. It's a really good example. So next, so on Wednesday, I'm going to randomly draw some lines and let you draw the cross-sectional views on that. Okay, I'm going to just directly draw it over here. And then we have 2 following examples to practice with all the layer examples. And eventually at the end of the lecture on Wednesday, you guys are expecting a quiz on that. So study this a little bit, study the layer here a little bit. And also during the lecture on Wednesday, you'll practice more. And then at the end, I think you guys will be prepared for the quiz. Let's see. I don't know yet.
So, are we like labeling the pictures, or are we like making like different views of the pictures?
You are drawing cross-sectional views.